In this video, we'll talk about what's known as regions of known cross-sections. And to demonstrate this idea, I really do just want to dive right into an example. So we're going to consider the region in the first quadrant bounded by y equals x squared and y equals x. So we'll call this R. And we're going to assume that this region R is the base of a solid whose cross-sections are squares perpendicular to the x-axis. Let's find the volume of the solid. So to begin with, I will say sometimes these are a little bit harder to visualize in terms of what that three-dimensional solid would look like. What's most important though is that you have an idea of the base region and the shape of the cross sections. So perpendicular to the x-axis is really indicating that we're of course slicing then perpendicular to the x-axis. And again, as we've seen before, automatically I know that that's going to involve integrating with respect to x. So by telling us that the cross sections are squares, that tells me what kind of shape, three-dimensional shape, we're going to get with this slicing method. We've seen with rotation, we always end up with either a cylinder or a cylinder with a small cylinder in the middle cut out. But here we have a completely different shape that's going to come then with our knowledge of what's the area of a square. So to go through this, what we want to think of is that the same process applies. Delta x here would be the length of my interval of x values, 1 minus 0 over n. And we know then that xk would be 0 plus k delta x, so k over n. Now, what I want to think about is what's the volume of one of these slices. So here, this very much depends on the description of the fact that these slices are squares. So if I were to think about the shape, let's see if I can sketch this somewhere, maybe use a different color. If I were to think of what kind of shape I would get out of this, we would get like a very smushed cube, if we're going to think about that. Not quite a cube then, rectangular prism. So the square that we have here on the both sides is dictated by that slice. And this dimension is coming from delta x. So I've kind of turned it on its side. Now, once I see that, that helps me think about how to find the volume of something like that. So the volume of that would be multiplying the dimension delta x times the area of the square that sits on the top or the bottom. So think about that as side k squared times delta x. Now, of course, then what we have to do is determine what the side is here. Well, the side, you'll note, is kind of this line here, is completely determined by the distance between my two bounding functions. So if I want to get the side length, and we suppose this is xk, the side length we see is simply plugging xk into the top function, y equals x, and subtracting what we get when we plug xk into the bottom function, y equals x squared. So that represents the side. We're squaring that because of our side squared formula and multiplying by that dimension delta x. So just like we've seen at this point, if I want to estimate the volume of the entire solid, we can simply add the volume of our indifferent slices. And if I want to then turn this into the exact volume, we simply take the limit as n goes to infinity. And what we get out of that is an definite integral. And this is against dx. My integrand is then we see x minus x squared quantity squared. Whoops, not a subscript. So again, the dependence on k goes away. And then once again, my bounds should dictate the range of x values. So I see that that's going to be 0 to 1. So notice we don't have a pi multiplier here because we don't have these circular kind of cross sections that we've seen when we rotate. And so beyond this, I can evaluate this. So this is x squared minus 2x cubed plus x to the fourth. So the antiderivative is x cubed over 3 minus 2/4 or 1/2 x to the fourth and plus x to the fifth over 5. We're evaluating this from x equals 0 to 1. So we get 1/3 minus 1/2 plus 1/5. And if I want to simplify that, the common denominator I could find here is 30. So this is now 10 minus 15 plus 6. And so we see that we actually get 1/30th for our volume. So to make sure this method is clear, let's take this same picture minus the square and think about different cross sections. So what if cross sections perpendicular to the x-axis are instead semicircles? So a lot of our setup will be the same. Delta x would be the same, xk would be the same. It's when we get to this step that the shape of the cross section mattered. And in that step, when it was a square, we squared the sides times delta x. But now if it's a semicircle, what we want to think about is that instead of having this square shape, of course, we'll have a half circle. So in that case, my volume of a slice will be different. So to get the area of a semicircle, we get pi over 2 times the radius squared. And then again, we would multiply that to get our three-dimensional volume here. We would multiply that by our delta x. So just like we saw before, what we have to pause and think about is how does this notion of radius correspond to what we have? So if I have a semicircle, so just by comparison, semicircle, we're looking at something like this. Notice that the radius is going to be half the distance between these two curves. So in substituting that in for a particular xk, the radius is going to be xk minus xk squared all over 2 squared. So that's substituting that in, and we get delta x. Again, the purpose of constructing this for a single slice is allowing me to see what the integrand would be. So when we want to find the exact volume, what I'm seeing here is I can get that with, here looking at this, we would have pi over 2 times the integral from 0 to 1 of x minus x squared over 2 all squared dx. So we get this integral in comparison to the one with the square cross sections. And so now what we want to think of is, again, kind of maybe simplifying this. So this is, notice when I square the 2, that's bringing out a 4. So collecting that without front, we have that. And then once again, this is x squared minus 2x cubed plus x to the fourth. Now that's the same integral we had above. So we know that this evaluates to 1 over 30. And so our final answer here, multiplying that by pi over 8, is pi over 240. So just in these situations, we have to be told the shape of the cross sections, and notice that the area of that shape is very much affecting then what the integrand ends up being. And also, typically when we're looking at that area, some dimension within there has to come from our knowledge of what the region is. What are the bounding curves? And then finally, the last thing I'll mention is that we have to be told how these cross sections are situated. In our example, we were told that it was perpendicular to the x-axis. If instead we were told to consider cross sections perpendicular to the y-axis, then you would integrate with respect to y. And notice that in that instance, now if I wanted to find a side length or a radius, we would take the curve x equals square root of y and subtract x equals y to get a side length, or half of that to get the radius. So kind of, again, thinking about orienting this appropriate to whatever your axis, or I shouldn't say axis because we're not rotating, whatever we're slicing perpendicular to, I should say instead. So in those instances, again, kind of think much like we did before, maybe drawing a representative slice, to be careful and make sure that you know which variable you're going to be integrating against.